Hey there, welcome back to Short Text 331. Today we're going to talk about the Fourier transform, and this is part 3 where we're going to talk about diffusion. So today I want to discuss this particular case of diffusion in free space in one spatial dimension. And this is our usual diffusion equation where I've taken the diffusion constant to be 1, so we don't have to worry about that. Of course, this could be typically not 1, but even if it wasn't, you could absorb it in x and play some games with the units and the scales so that you can convert your problem to this form. So our focus then is on this equation that has one time derivative, two spatial derivatives, and we need an initial condition and boundary conditions. Our boundaries are out at infinity, so we're just going to require our solution to be regular at infinity. And we need an initial condition for the time part, and this is going to look like this. This is going to be our assumption that there's some initial condition that looks like a profile of this form. It's a function of x. Here I show a function of x comma 0. 0 is our time. And so this is going to be our starting point, or something like this is the hypothesis. And the question then is, how does this profile, whatever it is, representing temperature or concentration of some chemical or whatever it is, how does that evolve as a function of time? And the rationale to solve this problem using Fourier transforms is the usual. That is that second derivatives of e to the ikx, this type of function, will give us ik quantity squared times e to the ikx. And so that is, of course, that e to the ikx is an eigenfunction of the second derivative operator for any value of k. In fact, k could even be complex, and this would still be an eigenfunction of the second derivative operator. And because of that, we propose the Fourier decomposition, also known as the superposition of these modes, e to the ikx, as our solution. So this is our proposed solution, f of x comma time, x comma t. The integral between is going to be the integral between minus infinity and infinity of some amplitudes that we don't know, we have to find out, and that f tilde of k comma t, which are the time-dependent Fourier transform of our target function, what we want to find, and then we're going to have, of course, the Fourier factor e to the ikx and the integral over dk. So again, we use this because it helps us solve for the spatial part, and then we have to find the space and time dependence of this f tilde of kt, so the k and the t dependence of this f tilde. Now, using our equation, our diffusion equation, we can take this form and insert it into our equation on both sides, on the left and on the right, and what we obtain on the left is simply that the time derivative hits this f tilde factor, whereas on the right, the spatial derivative will hit the Fourier factor e to the ikx and will bring down two factors of ik. So we have ik squared times our Fourier factor. And so what this tells us, these two Fourier representations being equal on both sides, given that e to the ikx is actually a function that is linearly independent for different values of k, so that simply tells us that this piece has to be equal to this piece over here. In other words, this first derivative of f tilde with respect to time has to be equal to ik squared times the function f tilde. And so what function do you know such that when you take one derivative with respect to a variable, in this case time, you get a factor times the same function? Well, that is, of course, an exponential. And so if you simplify the ik squared here and you write it as minus k squared, then you would obtain that the differential equation is simply that the time derivative is minus k squared times the function itself, and the solution to that is simply this. This is the genetic solution for f tilde. So f tilde of k comma t has to be f tilde of k 0 e to the minus k squared times the time variable. And so now this part, of course, encodes the initial conditions. When t is equal to 0, this factor becomes 1, and we're left with just f tilde of k comma 0. And that is actually assumed known, because remember, we're given f of x comma 0. We're given the initial profile that I schematically drew up here, which might look something like this, or something different, whatever you have in mind. And so if you do the Fourier transform of that function down here, you see down here, you have 1 over 2 pi integral between minus infinity and infinity f of x comma 0 e to the minus ikx dx. So this Fourier transform of our initial profile will give us f tilde of k comma 0. And so this then is what goes into the information that captures the solution of this time-dependent part of the problem. And so we can assume then that f tilde of k comma 0 is known. Again, by virtue of us just doing the Fourier transform of the initial profile, we get that information. So now that gives us pretty much everything we need, or at least enough to represent our solution, f of x comma t, as an integral from minus infinity to infinity of this initial condition, or rather this Fourier transform. Then we have this Gaussian factor characteristic of diffusion processes, e to the minus k squared time, and then e to the ikx, our Fourier factor, and then, of course, dk. So now our job is to do this integral for whatever it is that is given to us as f tilde of k comma 0. And so now we have to assume some initial condition, find f tilde of k comma 0, do this integral, and then we'll have the solution to our problem. So as an example, suppose that we're given this type of simplified case where the f of x comma 0, the initial profile is so concentrated around a point, which that means that we can model it as a delta function. Suppose then that our function is essentially 0 everywhere except at one point where somebody hits the system with a hammer or inserts a high concentration of chemicals or whatever it is, but the majority of it, of whatever is happening in the system at time equals 0 is happening around this point x equal to a. So if that's true, then what we need to do is to go up here and calculate f tilde of k comma 0. So we insert our delta function over here, and of course the result is simply 1 over 2 pi e to the minus I k a, because our delta saturates at a, and so that's where I wrote here. So this is simply the result of doing the Fourier transform of our initial condition. So we have now f tilde of k comma 0, we can insert it in our solution over here, and so if I write down our solution for this case is simply f of x t equals to 1 over 2 pi square root, integral between minus infinity and infinity of e to the minus k squared t and e to the I k x minus a dk. And so now we have to do this integral. Now, this integral has this Gaussian factor, which, as I was saying, is characteristic of diffusion processes, and then we have our Fourier factor here, e to the I k x, but now it's shifted by a because of our delta function that gives us our initial condition. Now, how do we do this integral? Fortunately, we saw this last time and also in previous videos, that the way to tackle these Gaussian integrals with a linear term in our variable, here the variable is k, is to complete the square. And so if you complete the square, you have that, the way to do it, the way I like to do it, is to separate this k squared t, put aside the minus sign, and so bring forward this part as well, and so we have k squared t minus I k x minus a, all that in the exponent, so this is my exponent. And so I separate the time variable because it's multiplying k squared, and then whatever's left is here. It's this k squared, and then I write minus I k x minus a, minus I k x minus a, but I multiply by 2 and divide by 2 and divide by this t that I took as a common factor over here, because that t, of course, doesn't appear on this second factor. So now we have this in a position where we know what we need to add and subtract to complete the square. So there's a 2k, of this case, the same k that appears here, and this factor is what we need to add and subtract as a square in order to complete the square. So I add that plus I x minus a 2t quantity squared. So this is now what's going to be our perfect square. But if I add this, I have to subtract it, of course, because it wasn't there before. And so now we go to the next line. This the first three terms are written as this perfect square. We have k minus I x minus a over 2t quantity squared multiplied by t, because this t multiplies everything, and then I take this factor here and I have a minus sign, I have an I squared, which could give me another minus sign, so that's a plus sign here, and then I have x minus a quantity squared divided by 4t. Why t and not t squared? Because again we had this t multiplying overall, and I already did that simplification over here. So then that tells us that our equation, our integral that we need to do, has its k dependence entirely concentrated in this perfect square. So then when I write it in the solution, looks like this. F of xt is 1 over 2 pi, and integral from minus infinity to infinity, e to the minus t and our perfect square that we have from here. And then we have, that's where the integral ends, by the way. This whole thing needs to be integrated. It's my Gaussian integral. And I'm going to switch variables from k to k prime, say, by shifting this variable k by minus I x minus a divided by 2t. That's going to give me a Gaussian integral that I know how to do. And then on top of that, I have this extra factor here coming from this term, x minus a squared divided by 4t. And that's just e to the minus x minus a quantity squared divided by 4t. So this Gaussian factor does not depend on k at all, and so it pops out of the integral, and it gives me the x dependence of the solution at the end. There's some time dependence here, but there will also be some time dependence coming from up here. So let's see what that looks like. If I were to go ahead and do that integral, then I would get, for the solution, f of x comma t, I get 1 over 2 pi, that's just along for the ride. And this integral is simply a Gaussian integral of width square root of t. And so if I account for that, then I will see that the result of doing this integral, as we've seen in previous videos, is simply square root of pi divided by t. So this is my factor coming from doing the integral, this Gaussian integral. So square root of pi divided by t. And this factor, this Gaussian factor in x, now is along for the ride. So this is basically all there is. This is our delta of x minus a diffusing as a function of time. If I take the time to 0, I see that this will go to infinity. This will become a narrower Gaussian factor, and eventually this will converge as t goes to 0 to my initial condition. Correctly, as I would expect, it will converge to a delta of x minus a. So this is centered around x equal to a. Now, at times greater than 0, then you see that what we have is a Gaussian. It's a Gaussian, and you see that the maximum height that is achieved at x equal to a is given by this factor here, 1 over 2 pi, square root of pi over t. And so this factor here then will tell me that the maximum height will decrease with time. So imagine that I have then, after time equals 0, at time greater than 0, I have a Gaussian centered at x minus a, and its height will decrease, its maximum height will decrease with time. It becomes flatter and flatter. Not only that, it really becomes flatter and flatter because this the width of the Gaussian, which is given by 2, it's given by 2 square root t, that increases with time. So not only is it becoming shorter and shorter, it's also spreading out. And that's the diffusion. That's the diffusion in 1D. It's not just at the peak of the Gaussian is becoming shorter and shorter. It's also becoming a very broad Gaussian as time goes by. And so that's really the behavior that you would expect from a diffusion process. In other words, if I were to go back and look at my my initial condition, it's going to turn into a Gaussian. It's going to become flatter and flatter and spread out, and eventually become very, very, very flat everywhere and spread out across the whole real line. Now, you might say, well, in the end, it's going to be 0 everywhere. Yes. However, if you do the integral from minus infinity to infinity of f of x comma t, then you will find that the integral, the result of doing the integral is just 1. It's time independent. In other words, the amount of stuff that I have diffusing it spreads out along the whole real line, but always preserving the integral of f of x as a function of time, which in this case, of course, is 1. The integral of the delta is just 1. And so if I spread it out over time according to my diffusion equation, then you will find that the amount of stuff that is being spread is still preserved. Nothing is lost, and that's reflected in this integral being 1, being time independent. That's basically the end of this exercise, of this particular example. Now you could generalize this problem and look at what happens if my initial condition is just a Gaussian. Suppose that f of x comma 0 is just e to the minus x squared. So how do we proceed? Well, the first thing you need to do, as we did before, is to write f tilde of k comma 0. You need to find this Fourier transform of my initial condition. Then from there, we can insert that in our general form of f of x comma t. And so that the general form of our full solution. And then from there, we can try to do the integral, which in this case will be some flavor of a Gaussian integral. And we can then analyze the solution and how it behaves as a function of time and x, as a function of time and space. And I will leave this as an exercise for you to do. It's not difficult. It's just more Gaussian integrals of the same type that we've done so far here and in previous videos. And so I think you can do it. And I think you can learn a lot from doing that. If you enjoyed this video and our videos generally in this channel, please consider liking and subscribing. And as always, if you're looking for a tutor in physics or math, either in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. And I'll see you next time.